Yeah, hi Karthik. Is my screen visible?
Yeah, Santosh.
Okay, let's start with today's session. So just a quick recap. So in the last session regarding the SVM, we have discussed mainly about the soft margin uh, equation, right?
Yes, yes.
So initially we studied about the hard
Hard.
margin, but since it is difficult to have, perfectly classifiable data by default, right? So that's
Hmm.
why we had the hard margin where we are okay with few misclassifications. Okay.
Yes.
But how many misclassifications and what is the length of each misclassification? We discussed all those details with the help of C and this theta parameter, right?
Yeah.
And then finally, we also went through this loss function for three different cases for a perfect classification and for a marginal classification where it will be in between the margin and the hyperplane, and for the incorrect classification, which will be the other side of the margin plane where it is incorrect classification. Agree?
Yeah.
And then we have seen this is a final equation and the summary. And also finally, we understood that gradient descent is the one again which will help us to find out the optimal values of W and B, which are which are useful to find out the equation of the plane. Okay.
Yes. Yeah.
So these are the fundamentals of SVM, right? So and also we have seen one scenario where if given two planes, how you will choose which plane as the hyperplane.
Correct.
Correct, which will have the least distance or
Yeah.
minimum 2 by W. Okay,
Hmm.
fine. So this covers the fundamentals. So the only few things are left. So one is the concept of kernels, which concludes the theory part of SVM, and then we will see coding, okay, and hyperparameter, and if there are any advantages and disadvantages of SVM. Okay, so
Yeah.
let's start with this concept of kernels. Okay, so to start with, kernels itself is actually a very big concept which involves a lot of math. Okay, so there is huge amount of maths that is involved in this, but we are not going into that level of depth. Okay, I can give you some resources which you can go through, but as for the beginner stage, I think if you understand basics of kernel, that is enough as of now. Okay,
Okay.
once if you want, if you get a chance to work on SVM, then you can start digging deeper. Okay,
Okay.
so let's try to understand basics of what does a SVM kernel mean. So one very important factor of SVM is it is very helpful to deal with data of multidimensional, Karthik. Okay, so this is one of the major point which differentiates SVM from other algorithms. Okay, if we have seen logistic regression, right? So that is great, but it is only applicable for 2D data
Okay.
or
Yes.
3D. And what I mean by 2D data is that should be linearly separable by default.
Yes.
Only if it is linearly separable, it can have four or five dimensions where right? So here each dimension is considered as, sorry, each feature is considered as one dimension. So if you're having
Yes.
five features, so five dimensional data, even if it is there, it should be linearly separable. Only then we can use the linear regression. Sorry,
Yeah.
logistic regression. My bad. Okay. But coming to SVM, the one beauty of SVM is even though by default the data is not linearly separable, still SVM can work on those data set, okay, by using something called as kernel and kernel trick.
Okay.
Okay. So if you see, it's a what is a kernel? It's a mathematical function which helps organize data and make it easier to classify. The primary goal of SVM is to find out a hyperplane. But in most
Yes.
real cases, this data is not linearly separable. Okay, so
Yes.
by default it is not linearly separable. So by default you cannot find out the equation of the plane.
Yeah.
Okay. Because at the end of the day, whatever is shape of the data, so SVM goal is to find out a hyperplane. Okay, plane is usually a straight plane. Okay, not any curve. Fine. If it is in a 2D line, 3D plane, 4D hyperplane, but anything
Yeah.
is straight, not like curved structure. Okay. So to do that, first of all, the data should be separable. Okay. So in that scenarios, so what we do here is kernels help us implicitly mapping the original feature into a higher space where it is more easily separable. So that means, for example, if you see this is the data, okay, it's
Yeah.
2D. Okay, but if you see in the 3D, that means I hope you are able to
Correct,
visualize
correct. Yes, yes.
from top angle, or if you see it from the bottom angle. Okay.
Yeah.
So then those gets mapped into, okay,
Two
like
different.
different
Yeah.
spaces, right?
Correct.
In that case, you can cut it in the middle.
Yes.
Okay, so that these
Yes.
can be separated. Okay, this is just a simple example, right? For example, if you have two features, let's say height and weight. Okay, in the original space, there could be 2D. Okay, but you use some kernel. Okay, what is, first of all, what is kernel? Kernel in simple terms is, it's a function, math function, okay, which helps, just give me one second, yeah, which helps to convert a given point from 2D, okay, into some higher dimension, let's say 3D. Okay, you can convert into any higher dimension. Okay, so that means what? We are given a data set, okay, that usually will be in 2D. If it is by default separable, we are happy. If it is not, right, so then we'll try to, map this data set into some higher dimensional, okay,
Yeah.
so that it could be separable over there. If not, we will see some other kernel trick where it will, do some other type of transformation and into some other dimension. Fine.
Okay.
So basically, it's a function. That means what? Over here, you see all these data points, okay, blue and red. Let's say combined, we are having 100 data points. Okay.
Okay.
Now, all this, each and every data point, okay, if you apply some function on top of that, it gets converted into 3D. Okay. Let's say this point is this point, as an example, something. Okay. This one of the red point is now this point. Okay. So, like that, when you pass a function, okay, let's say kernel, one second. Yeah, let's say we are having a kernel function. Okay, just as what is just a simple function. For example, let's say f of x equal to what is this x square? What is this? Is a simple function. If you give
Yeah.
two, answer is 4, right? Square function. This is simple square function. It's a math function.
Yeah.
Similarly, kernel is also a function where it will take the input as an input data as an its input, and it will give you output as new dimensional coordinates. That means, for
Okay.
example, if you go x comma y, which is 2D, that's why you're having two values, kernel function will give you three dimensions, x, y, z.
Okay.
Okay. So these three are the coordinates in 3D space.
Okay.
Fine. So now you are having same number of points, but now mapped in a new dimension, 3D dimension.
Yes.
Okay. Getting?
Got it. Yeah.
Fine. So we'll see one example, like let's say we have something called as SVM, second degree polynomial mapping. So over here, if you see, uh, we are having, let's say we have this point, okay, some function, okay, plane equation of plane x of x comma y. So this, if you want to, which is in 2D, okay. So now if you apply, okay, some kernel, its corresponding points in 3D are these. Okay,
Okay.
that means what? So, for example, you have normal plane, okay, x-axis, y-axis. You have some 2 comma 3 point. This is 2D. Agree?
Yes.
Why 2D? Because we are having only 2 point,
2 points.
two values. Each
Yeah.
value represent one dimension, right? This
Yeah.
is
Yeah.
the
Yeah.
value of x.
2
This is for
points.
y. Now, if I want its corresponding point in 3D, okay, just like this. This is 2D. In 3D, what will be its point? So, if you use this one, so this will be x square. That means 2 square 4, comma square root of 2 into 3 to the 6, okay, comma y square 9, okay. So 4 comma 6 root 2 comma 9
Hmm.
are its new coordinates in 3D.
Yeah. Yeah. Got it.
X-axis coordinate, y-axis coordinate, z-axis coordinate. Okay, you'll have three
Okay.
coordinates, right? See, this is x, this is y, this is z.
Yes.
Okay, so that is, these will be the new coordinates. Okay, so this is a kernel function will give you this. Okay, so when you pass in this one, okay, a kernel function will give you the output in this way.
Yeah.
Okay, fine. But now the point is, this is fine. But the point, the one problem here is, if you are having 10 points, okay, you can do these calculations and get 10 corresponding points in 3D. But if you have huge number of points, okay, let's say
Okay.
you have some 10,000 points, okay. So computing this is very cost effective, okay, not
Okay.
cost expensive. Okay, so it is very expensive to compute, these values for, let's say, 10,000 points.
Yeah.
That's why you have something called as kernel trick.
Okay.
Okay, so kernel is a function, but because sometimes it is very costly to perform these operations, we have something called as kernel trick. Okay, so basically what it does is, let's say, okay, so you are having this is a point, right? So this is one of the kernel function, Karthik. Okay, so we have many kernel functions. Okay, so this is one of the kernel functions. So to perform this kernel function, okay, so usually if you want to use this formula, what we do, let's say A and B are 2 points. Okay,
Okay.
so what do I mean? Let's say A equal to uh, A1 comma A2. Why? Because as of now we are in 2D. So
Yeah.
point will have two values, right? Just like X and Y. I'm considering A1 and A2. Getting?
Yeah.
P is another point, B1, B2. You can also say XY, X1, Y1, X2, Y2, or XY, X1, X2, X2, Y1, Y2, anything. Okay. So
Yes.
A is 1 point and its X value is A1, Y value is A2. B is another point, its X value is B1, Y value is B2. Okay. Now these are the points, and I want to find out these points corresponding points in the 3D.
Okay.
Okay.
Hmm.
So what we'll do, so if this is the equation, so if a point is in 2D, its corresponding value in 3D will be this. So if I apply the same thing, okay, so if you use this formula, okay, the phi of A is what, x square. In our, if you consider the point A, what is our x? A1. What is our y? A2.
A2.
Correct. So it will
Hmm.
be A1 square root of 2 A1 A2
AB, A1, A2,
comma A2 square.
A2 square.
Okay,
Yeah.
that is a value. And we are doing transpose. Okay, so you got transpose. Okay, dot product of, for another point B. Okay, B is what, B1, B2. If you replace this, you are going to have these two.
Hmm.
Okay, so this is a kernel function we are doing, and it is going to give output in this format. So if you consider these points, these are the values. And if you solve this, so this is, so you will multiply A1 square plus B1 square. Okay, this multiplication. Okay, and
Yeah.
square root of 2 A1 A2 into square root of B1 B2. So it will be square root of 2 whole square will be 2 A1 A2 plus B1 B2. Okay, and A2 square into B2 square, it is A2 square B2 square.
Yeah.
Okay, now because this is transpose, so this when you do transpose, it will become in this format. Okay, this will be in this format. That means we'll have B1, this will be same. Okay, but imagine this as transpose means vertical will become horizontal.
Yes.
Okay, so it will be like this with like this. Okay, the first element with first element, second element with second element, third element with third.
Yeah.
Okay, so you got this, and this can be simply written as A1 B1 plus A2 B2 whole square, A plus B whole square.
Correct. Correct.
To do this
Yeah.
thing,
Yeah.
and this can be written in this format. Okay, it's matrices formula, and finally you can, this can be written as this format. Okay,
Okay.
now the important point is, this is telling us, instead of doing this computation, okay, for this computation mainly, for every point, instead of doing all this computation A1 square, calculating square 2, I can simply take the dot product of these two values. Okay, you are having A, you are having B. If you just take dot product of A transpose dot B and do square of this, the value you are going to get, okay, will be the new coordinates for this A and B in a 3D.
Okay.
Okay, so instead of doing all this, we are going to do this. Okay, so it's a simple math trick, so that's why it's called kernel trick. Okay, so
Yeah.
it is helping us to, bypass the complex computations, okay, which
Got it.
require heavy resources. Okay, so in this is one way, but there are many kernels actually. Okay, one type of kernel is, okay, this is the equation of the kernel, and it is just saying, instead of doing this, I'll just directly do this. Okay, give me 2 points. If I find out the dot product of those, the value will be, the new values are going to be the values in the 3D. Okay, like that, if
Yeah.
you do for every point, okay, every point, you'll get the new points in 3D.
Got
Okay,
it.
so that's how, and you can see if that, and if you plot this new point, okay, and see if it is separable by any plane or not. Okay, so if it is not, then you can do two things. One, use some other kernel, or go for 4D.
Okay.
Okay, increase the dimension or go for another new kernel. Okay, so this way, okay, you can deal with, higher dimension data. And
Okay.
Usually we have different many there are many types, but most common are four. Okay, you will come across. One is linear, and its corresponding equation is this x1 into x2. So by that means we are not doing any transformation at all. Whatever the value we are giving, that's just doing the dot product. Okay, so it's called simple linear. Okay, and next you have polynomial. You have Gaussian, or it is also called as RBF, radial basis function, and sigmoid. Okay, so one thing is, as I said, we are not going into details. Okay, of this kernels, okay, because this covers, might take 1 hour more, 2 sessions more. Okay, so what I'm trying to do is I'm just giving you a basic introduction of kernels as of now. Okay, in
Okay.
future time permits, then I will, take one more session on these kernels.
Yeah.
So but just in case if you start giving interviews, and if you come across any kernel question, so you can tell the basic definition of kernel. Okay, what is a kernel and why it is helpful, and how it will do the transformation, the basic transformation, and what are the different types of kernels which we are having. Okay, so I can share you as of now reference of few blogs. Okay, you can go through them and have some understanding, and in future we will again come back to these kernels. Okay.
Yeah.
Okay, fine. So that is one thing. Okay, and yeah, mostly this I would say is a theoretical part of SVM. Okay, and I would like to just show you some code. Fine. So if you just go, and I said code is always going to be very simple in ML. Fine. So as you know, these are the inputs which you are familiar as of by now. Fine.
Yeah.
So we are having this heart example. So we are having all these features, and we want to predict whether a person has heart attack or not. Okay,
Yeah.
or any cardiac attack or not. Basic inputs dividing the data. Okay, and the main thing is how you are importing the SVC. So what is SVC? Support vector classifier.
Mm.
Okay, so any new model, so first you need to go to its documentation. Just simply type sklearn SVC or SVM, so you will come to this page. Okay, so here it is saying, so as you know, every thing in Python is an object. That means it is imported from some class. Fine.
Yeah.
So over here also SVM, SVC is inside SVM, and inside SVM is inside sklearn. Okay. So in this package, in this module, you are having this SVC class. Fine. So sklearn SVM is support vector mission. In that mission, a specific thing is SVC, support vector
Mm.
class. We
Yeah.
also support vector regressor also. Okay. So as I said in previous class, that all these classification models are designed for classification purpose mainly,
Yeah.
but we can also perform regression. Okay, with small
Hmm.
tweaks. Fine. So basically, this is where how you can import. So or you can simply say from sklearn.svm, yeah, import SVC. So once you import SVC, let's basically see the basic training the model, and then we will go into details. For example, this is my SVC model. Okay, and I'm just saying model equal to SVC. Okay, that's it. So calling, creating object, and then I'm fitting, and prediction is done. Okay, and as of now I'll just do this. Okay, and then prediction. Okay, and if you see, uh, this is my accuracy, this is my confusion matrix. Okay, so what we have done here, so all these concepts which you're already familiar. So starting an object of model, passing in train data, test data, and you're passing in the X test for the predictions. Okay, you got the
Yeah.
prediction done. Once you got
Yeah.
the predictions, you are checking the accuracy score done. And once you got the accuracy score, we are not going to always rely on accuracy score, right? So what we're doing, so we have seen the matrix class. So we have the class confusion matrix, and we have the classification report. Fine.
Mm.
So in the confusion matrix, these are the values. Let's say these are 0 and 1. This is 0 and 1. Fine.
Yeah.
So this diagonal is a true diagonal. Okay. And these are
Yeah.
false values. Okay.
Faster.
Correct. So there are some misclassifications that are happening. Okay, fine.
Yeah.
And this is a classification report for zero. What is the precision? What is the recall? F1 score, micro, all these things we have discussed detail in our classification metrics class. Okay. So you can see the precision, what is the recall for one, what is the F1 score? Overall F1 score is 0.73. Okay, fine.
Yes.
So this is how you can simply check the SVM metrics also. This is a basic
Yeah.
thing. Now coming to the main thing, that is called as, for any model, you have something called as hyperparameters.
Hmm.
Okay. So yeah. So if you see the hyperparameters of SVC, over here. Yeah. So these are all the yeah, all these are hyperparameters. As I said, what are these hyperparameters? These are just like a tuning knobs of each and every model. Okay. So once you change any of this, the model will behave slightly differently. It's the
Yeah.
again it's the SVM model itself, but its nature will be a bit different. Correct?
Yeah.
Fine.
Correct.
So these are different hyperparameters. As I said, all these are not you don't touch all of this, okay, all the time. Okay, some are by default, but mainly what is C? One is C is the one thing, so which is called as regulation parameter. Okay, yeah, but we'll come to this in one moment. Okay, but before that, um, let me see if we have anything. Okay, yeah. So now when I ran this model, Karthik, okay, so I did not use any hyperparameters. You see, I just said SVC.
Yeah.
Okay. But by default, there will be a default hyperparameter for every parameter.
Yeah.
Okay. So even though I did not give anything, so but this model has all these values, but default values. Okay.
Mm.
And if you want to see those default values, you can just do model.get params. Not only for
Okay.
HPC, any other model also. When you just do model.get params, okay. So these are the default values.
Yeah.
Okay. So all these parameters are present to this our model.
Mm.
So now, if you see now, going to the hyperparameters, yeah, I have noted down these hyperparameters over here. So by default, we have given one.
Yeah.
We don't give anything by default. It has taken one. Okay, but why? Because if you see here, what is C initially? C is a C is a regularization parameter. Okay,
Okay.
so we have studied over here. What is C? Yeah, C is a regularization parameter, and
Mm.
it is inversely related to
Uh,
regularization.
regularization. Yeah.
Right? That means what? If you increase C, regularization will
Will
decrease.
decrease.
Okay. And for example, if you decrease C, regularization will increase.
Increase.
If
Yeah.
more
Overfitting.
regularization, then what will happen? There will be,
Overfit. Overfitting.
yeah, there will be less overfitting. Regularization is
Okay.
used to control the overfitting, right?
Controlled overfitting. Yeah.
Right.
Okay.
So, yeah. So if you decrease the C, regularization will increase. More
Yeah.
regularization means we are more regularizing. That means we are
Yeah.
controlling the
Less chance of. Yeah. Less chance of. Yeah.
okay. So if you are controlling the overfitting, it is the chances of working on our training data. In training data, it might what happens? Okay, when we increase the regulation, so the model overfitting will reduce. Okay,
Correct.
so if there is no overfitting, what can happen on the training data set? There could be some issues, but on the test data set, we'll get good results.
Yes.
Okay. Yeah, the other way around, what happens if I'm increasing C, R will decrease. That means regularization is decreasing. That means I'm not controlling the overfitting. That means what? There are chances of getting overfitted.
Yeah.
Okay, that means what? Model is getting overfitted means what? On trained data set, it is working very well because it is almost overfitting. But the problem is on test data set, it might face some issues. Okay, so what? This is a long thing, long story. But if you just try to make it short, one or two things
Yes.
you can remember. If C increases, okay, if C,
Are we?
yeah, no, if C is increasing, R is decreasing, like regularization is decreasing, means more
Yeah.
overfitting. More overfitting means the variance is more. That means what? Our test accuracy will decrease.
Yes.
More variance means what? Variance is related to new data, that is test data.
Yes.
If
Yes.
and variance is error. Bias and variance are errors, right?
Yes.
So
Yes.
more variance means more error on the new data, that is test data. More error
Test
means
data.
test accuracy.
Yeah.
Okay? So in simple words, C increase, test accuracy decrease, and C decrease, test accuracy increase.
Increase.
These are the two things. Okay. Fine. So now if we go back to the coding part, so we have this default parameters. Okay. And now, for example, instead of using this model, so what I will do is I'll go for C equal to some 0.2. Okay. So now this is my new model.
Mm.
And if I run the accuracy, uh, yeah. What is this prediction of zero? Let me put it here. Okay. We'll try with different examples. C is 2. My accuracy is 72.
Yeah.
Okay. So That means what? If I'm increasing the C, uh, I'm decreasing the regularization. It should have more variance. That means the error on this should be more. Are we getting the same results, or are we getting the opposite? Uh, yeah. So if we are decreasing the value of
C
C, our
accuracy is decreasing.
accuracy is decreasing. That means what?
Yeah,
My variance is increasing.
correct.
Okay. And in other way around, if I'm going for, let's say, from 10, C equal to 10, uh, I'm saying regularization. My what is this white test? Training on this white test vibrate. Okay, it is increasing. Okay, so I think it is working fine, but uh, is it complying with C? We'll see. Okay, but anyways, that is one parameter. Okay,
Yeah,
C is which will control the regularization.
yes.
Okay, and second thing is a kernel part. Okay, so one is a C, which will, the strength of regulation is inversely proportional to C, must be strictly, this should be positive, etc. And kernel is, what type of kernel you want to use if you want to transform your data. Okay, whether it is linear or polynomial or RBF, sigmoid, or some other pre-computed means if you want to give your own math function.
Yeah,
So each
okay.
of these will have its own function, right?
Hmm.
I've shown you in the kernel. So each of these are all its own function.
Correct. Yeah.
Right. So, but if you don't want to use those four, if you want have your own function, you can
Hmm.
use this and provide your function.
Okay.
Okay. And what is the degree of the polynomial, to which degree you want to convert? So that is this degree. Okay. And gamma is the value present in this one of the equation. Okay. You see this gamma,
Yes.
this one. So that is the gamma over here. It is saying the kernel coefficient. Okay. By default, there are some values. And this is coefficient, and this is shrinking, we don't touch. And probability, yeah. So probability is whether to enable probability estimates or not. Okay, that means what, in logistic regression, so we got probabilities for each and every prediction. Okay, that means our model might predict. That means
Yeah.
when you pass, this is our model, right? So when you pass some input, okay, if there are output classes as 0 or 1, so the model can predict 0 or 1. Okay,
Yeah.
let's say it has predicted 1.
Hmm.
Okay, but what is the probability of predicting 1? Fine. So if for example, when it does the prediction, so it will say, it will divide, it will see, okay, there are 30% probability for the input to become 1 0, and remaining 70% of 1. So because
Yeah.
70 greater than 30, final answer is 1. Agree?
Yes.
But it will be never like 100 0. Correct?
Yes.
So there will be some probability for this also, but whichever the higher probability, that will become the prediction. Fine. So
Yeah.
if you want to see the internal probabilities, you can do this. Okay. There is some function called as predict proba. Okay. So
Okay.
over here, if you see in the hyperparameters, you have, where is this probability? Yeah, probability you have, right? False. So by default,
False.
it will be false. Okay. By default, it will be false, but you can do it as true. Fine.
Okay.
So, but if you don't do true, for example, I am not using anything. Okay. uh, I'm just running the model. Now,
Hmm.
if I'm that one is, you can use the predict function. Okay, the model is ready. You can use the predict function. I'm passing first record from X test.
Okay.
Following the code. So this is
Hmm.
my X test. I 0. I'm saying right.
Yeah. Yeah.
This is my first record in the test set. I am passing this and I'm asking the predict. That means
Hmm.
whether it is 0 or 1, just tell me.
Hmm.
Okay, when I pass this, the model is saying 0.
Yeah.
Okay, but I don't know in the backside what was the probability of 0.
Hmm.
Okay, there are two classes, 0 and 1.
Correct. Correct.
For this, the model is saying the prediction is 0. Okay, that's fine. But what is the probability of this? And what is the probability?
Yeah. Yes.
Okay, because why it is important is, for example, if the probability of this is, let's say, 51, and for this it is 49,
Correct.
it is not a great classification, right?
Yes.
Just with 1%, the model is saying this.
Yes.
Okay, but if it is 99, or maybe if it is 20, 80, and if it is some 20, that's okay,
Yes.
we can say. But if it is very marginal classification, then there are chances like if we change something, then this could become 1.
Yes.
Correct. So that's why it is important to see the probabilities also. But to do that, you need to act. You need to first set it to true. Here
Yeah,
by
probability equal to.
false. Okay. I can get only prediction. But if I
Hmm.
try to go for predict proba, okay,
Okay.
that means this will give you probabilities. If I
Okay.
do this, it will give you error. Okay, it is saying
Hmm.
since you have kept it as false.
False. Okay.
Okay. So now if
Got
I
it.
just do
True.
true, okay, and now if I calculate the accuracy, that is same. And here also I can go with the prediction is 0. But now if I do this, it is saying, see, this is 0th accuracy, this is accuracy for 1. Okay,
Okay.
90% it is 0 probability, and 1 and 9%, almost 10% it is for 1. That's why the probability is 0.
Zero.
Not
Okay.
the output is 0.
Okay.
Getting any
Yeah.
question? Okay.
No.
Similarly, we'll see one example where we get the output as 1. So
No.
then
Okay.
this value should be more. Agree? Because this is the probability of 1.
Yes.
Only when this value is more, then the output will be 1. If this value is more, output will be 0.
Yes.
Okay. So I don't know which one I'm just trying. Oh yeah. So for 10th example, that means this row. When I show 10, yeah, this is a row
Hmm.
for which the model is saying 1 as
One.
a, okay. This 1 is what? The class
Yes.
you have, right?
Zero one. Yes. Yes.
Fine.
Target.
Yeah, so this is 1. But now what are the probabilities? Now if I pass 10 here, yeah, now you see,
78%. Yeah.
okay, so now 78 for 1 is greater than 21 for 0.
Zero.
So that's why it is saying as 1. Got it?
Yeah.
Okay, so checking this probability is also very, very important. Okay,
Okay.
fine. So, but for that, you need to put this hyperparameter as true. Okay, so now you are getting right. So, because SVC without probability equal to false is one model, and SVC with probability equal to true is one model. Correct?
Correct. Yes.
But there is very small difference between these two models. Both are SVC so only. Okay.
Yeah.
Predictions, everything is fine. But if you keep it as true, it is having one more small power, that is giving out probabilities also.
Yeah. One more extra checking.
Extra
Yeah.
checking, like extra output, it is able to.
Out. Yeah.
Okay. So, and like that, each hyperparameter will have its own functionality. Okay. So
Okay.
changing C will change the values. Okay.
Hmm.
For example, if you see by default, it is 1, right? So with
Yeah.
1, the accuracy is 73. Now,
Hmm.
accuracy is 73. Now, if you go and do this classification matrix, we are having 6144, this one value. Now, if
Hmm.
I come here and change the value of, let's say, 10, okay, now the accuracy is changing 75. Now,
Hmm.
if I go check the classification matrix also, it is 6144, or for example, you see this value 0.73, right?
Yeah. Yeah.
If I run this, see,
Yeah.
it
Zero
is 7.
seven six. Seven.
Agree?
Yeah.
Every parameter, whatever you are using here, is going to affect your final output.
Correct.
Okay, so that's why you should be careful and understand how it is impacting. Now, if I'm decreasing this, the accuracy is changing. Okay, and now here, if you see, the values are also changing. Right,
Yeah.
right. So that is the one. So mainly, C is one thing you need to understand. Okay, and this is by default, by default. Okay, degree we have seen gamma kernels, and max iter. Max iter is nothing but how many iterations it will do. Okay, for example, if you see here, hard limit on iterations within solver, or for no limit. That means solver is what? Solver, I think we have seen in the logistic regression. So over here, where is this? For example, if I go to SQL and logistic regression and go here, and over here there will be something called as solver. Okay, uh, the algorithm to use in the optimization problem. So what is how we are doing this using gradient descent? We are performing, right? So there are different types of algorithms. Okay, internally how to perform that. So with each of the we have seen these examples, right? So over there it will do what do I say, uh, how many times it should check for the optimal value. Okay, so over here when you're having where is this yeah, hard limit of iterations within the solver. So first it will find out some random value w and b. Agree?
Okay.
With that, it will find out, it will give it a line. After that, it will change the values. Then it will keep on repeating the loop, right?
Yes, yes, yes.
You know that loop. Okay.
Yeah.
So how many iterations it should do?
Okay.
100, 500. It depends. Okay. If you want
Hmm.
to set a limit, you can limit. But usually we
Okay.
will not touch this. We'll say, I don't want to know how many iterations. Still, you will get the best plane. You don't
Yeah,
stop.
yeah, yeah.
That is no limit. For that, you need to give -1.
Okay.
Okay. By
That is
default,
fine.
it
Yeah.
is. Okay. Probability we have seen.
Hmm.
Okay, random state, nothing. Shrinking to these values, we don't use much. Okay, and what is
Okay.
the? We have seen some shrinking. What is shrinking? Whether do shrinking steric? I'm not sure what is this. As I said, we will not touch all of this. Okay, only few of the parameters we will control. Fine. These are the hyperparameters. Now coming to the attributes. Okay, you know the difference between parameters and attributes. While you are building the model, you use hyperparameters. Okay. Now the model is done. We got the model. Fine. So with this model, we need to use this model, right? Fine. So we have just seen two ways of using. One is predict using predict. One is predict proba. Getting?
Yes.
Okay. So the other ways also. For example, if you see here, uh, we can say model dot class weight, model dot classes. Okay. All these things you can do. Fine. So for example, what is our model? Our model is SVC model dot. If you just give dot and tab, it will give you all this. Okay. Class weight. Uh, we did not give any weight or what. Okay, so class not this dot class weight. Okay, weightage of this is same, and if I the model dot coefficient, this is not having coefficient. Okay, what parameter shall we see? Classes we'll see. Okay, there are two classes. uh are we having the intercept? Yeah, this is an intercept. Okay, and okay, what is this coefficient? Sure. Okay, this is only available with some linear kernel, it seems. Find support. Oh, okay. So this is interesting. So what these are the indices of the support vectors, man. Okay. So that means in our data set, so some data points will become support vectors, right?
Yes.
You see this point. This point is
Yes.
support vector.
Yes.
All these are not support vectors. The one which is touching the plane is support
Oh,
vector. Agree?
correct. Yes.
Here also, this is also not touching, but just assume if it is touching, then it is support vector. Okay. So, so like that, in our case, okay. So if you want to support vectors, it's like support underscore. Okay. So when I do support underscore, it is saying these points are there are many points on the plane. So these are all the points of support vectors.
Got
Indices.
it.
Indices, that means row numbers. Okay.
Yes.
This is row number 0, 1, 2, 3, 4, right? So it is saying indices of the support vector. Getting?
Yeah.
Okay. In our case, I think there were many support vectors. Okay. The overall data set 1025. In that, we are having 743 support vectors. Okay. And support vectors ND array. So what is this? Support vectors array, I think. So okay, fine. So these are different hyperparameters. You can play with this. Fine. Uh, so that is you can that's how you can change this value and check the accuracies and decide the best set of hyperparameters. But usually we'll do with something called as grid set CV and random set CV. Okay, these are two tools packages which will help us to experiment and find out which is the best set of hyperparameters for the given data set. Okay, so have we covered this
Oh,
grid search and random search? Did we cover?
no.
No. Okay, fine. So we'll take one class on this. Okay, fine. So that is
Hyperparameters.
hyperparameters. Fine.
Yeah.
So lastly, we have something called as just some pros and cons of the this SVM model, Karthik. Okay. So
Yeah.
over here, if you see, mostly this will work well in high
Yeah.
dimension.
Higher dimensions. Yes.
Okay. So and we have effective with margin based separation. Okay.
Hmm.
It's a margin part, right? So that's why it is effective.
Yeah.
And versatile with kernel trick. Okay,
Hmm.
so which is related to this point, even for high dimensions and complex also we can do this. And memory efficient. Okay, memory efficient is why, because it only focuses on the support vectors. It doesn't care for all these points because it thinks if I am doing justice to the support vectors, anyhow all these points are getting automatically correctly classified. So
Correct.
it doesn't need to take care of each and every point.
Yes. Yes.
Okay. And if it avoids overfitting with right tuning, that means if you use perfect values of C, it will also control the overfitting.
Okay.
But now coming to this, not scalable to large data sets. Okay, that means what? If you are having large data sets, then uh, it will be little computationally expensive.
Mm-hmm.
Why? Because it need to do many computations. Even though we have kernels, even though
Yeah.
kernel tricks, but still, if you have like like very large data set and in very high dimensional data set, so converting the complete data set into new dimension is a bit you know heavy.
Okay.
Okay. And sensitive to outliers and noisy data. Yeah, this is important because
Because we don't have any outlier concept here. I mean, it will
yeah, yeah,
consider.
yeah, correct. But no, yeah, but see, the whole success of SVM lies on the support vectors. That's the reason it's called support,
Correct.
because it is focusing only on these 2 points and saying
Correct.
not 2 points, only on support vectors and saying I am focusing on this. Okay, and this is my plane.
Hmm.
So if these are perfect, I'm perfect.
Yeah.
The problem is if you are having outliers, for example, you are
Hmm.
having a data set and you have one data point here. Okay.
Yeah.
And if this is an outlier and if you're not checking this, and for example, if you pass like that, the model will consider this as a perfect point. It will draw a hyperplane over here with this.
Okay.
Okay. So, which is not proper, right?
Yeah.
Because this is an outlier. This is not the actual point.
Correct.
Correct. So that's why it is sensitive to outliers and noisy data. Okay. So if it's
Hmm.
a perfect point, it's good because it is
Yeah.
providing maximum separation from the other data point. Okay.
Correct.
If it is an outlier, okay, so it is not the actual point. So that's why the model might not be a perfect point.
Yeah.
Okay, fine. And you need to be careful while using kernel. Okay, so which kernel you want to use it, and parameter tuning it might require,
Hmm.
and requires feature scaling.
Okay.
Okay, so that means what? Because this is related to distance.
Okay.
Okay, so any model which involves distance needs to be scaled.
Okay.
Okay, so there are some models which does not rely on distance. We'll see them, but logistic regression is a distance based.
Okay.
Here also it is a distance based, right? So you are calculating the distance between from here to the maximum margin and the distance between this. The whole equation of the SVM is what? 2 by W.
Yeah. Yeah.
2 by W by 2, something. Yeah, W by 2. This is the distance. See here, we are calculating the distance between D1 and D2. D1 point and
Correct.
D2 point. So that's why they should be scaled.
Okay.
Okay. Scale means what? They should be bring to some proper scaling. Okay. That means it could be standard scaling, normalized scaling. What do you mean? For example, you are having a age column and you are having some income column. Okay. So age column is what? Usually it will be, let's say 30, 40, 50. The values will be like this. Okay.
Hmm.
In a IT company. And the income could be like, let's say 1 lakh, 2 lakh, okay, per monthly, or 50,000 or 40,000. Okay. 40,000. If you see the range of these values, this is a very small numbers compared to these big values.
Yeah.
Correct. So if you use them directly, okay, so then the model will not perform well.
Yeah.
Okay, because unnecessarily it will give more importance to bigger numbers.
Correct.
Okay, so that's why we will scale them. So we will scale them. That means bring them to some range, let's say between 0 to 1, and also bring these also between 0 to 1 scaling.
Okay.
We consider scaling, standardization, normalization. I think in statistics we have covered, I think. Okay, but I will also check once. If not, we can take that. Okay.
Okay.
So it will bringing into same scale is very, very important. Not
Okay.
only this model, always remember any model which involves distance. So this
Okay.
is very important. Okay. And no direct probability outputs. Okay. So that means it's not a con. We don't have direct, but we can use it, get it from predict proba. Okay. We have
Yeah.
probability. Using that we can get it. Okay. On overall, SM is, I would say, a great model, Karthik, which gives good accuracies. Okay. So which is very helpful in higher dimensional data also. Fine. So I just suggest you to once go through the documentation part over here and take any some data set, for example, this basic data set, some data set, and build a small model and change the mainly hyperparameters, play with these hyperparameters. Okay. And you can see how the values are varying. Okay.
Yeah.
Fine. Any questions?
No, so much.
Okay, fine. So I would say that concludes more or less the SVM, where we started with the basic intro theory and some basic intro of kernels, mainly the loss function part, how it is dividing, what are the parameters C, gamma, and we have seen basic code and hyperparameters. Okay, so I think
Okay.
as of now this is enough. Okay, and if anything is more is required, I will include that also. Okay, but I would say this is about the SVM. You can let me know
Oh,
if there are any questions, or else, yeah, that's for today's session.
yes.
Okay,
Yeah.
fine. Yeah. So next in next session, I'll just tell you what we're going to cover. So in next session, we are going to cover something called as KNN. Okay.
Okay.
So it is called as K nearest neighbor model. Fine. So in regression side, we have covered linear regression, right? In
Yes.
classification, we have covered logistic regression and SVM.
Hmm.
Okay. And now next we are going to cover KNN and
Okay.
some more algorithm. Next algorithm called as naive Bayes. Okay. So these
Hmm.
four models are almost independent of each other.
Okay.
So once we complete this, the next module is going to be on the tree models, okay, where you will have something called decision trees, random forest, and bagging, boosting, etc., etc. This is a complete module which is also coming under classification only, okay. But here
Okay.
the things will follow each other, follow one,
Okay.
okay. That means one. These are just extension of one concept from another concept. Fine.
Okay.
Then we'll see. But goal is to cover KNN and Navier next. Okay.
Sure.
In our next session, we'll start with the KNN. It's a very
Okay.
simple algorithm. I think SVM might be because it's involved a bit of math.
Vectors, yeah, everything.
Vectors, it might feel that it is a bit tough. Okay. But trust me, every other algorithm like KNN or naive Bayes will have some probability concepts. Okay. But KNN is very, very simple algorithm. And after that, tree based are very, very simple algorithms. Okay.
Okay.
Tree based and classic. And after that, clustering we have, right? In clustering, we have two, three algorithms. Those are also very, very simple and very, very interesting algorithms, I would say.
Okay.
So we'll have fun. Fine. Let's meet for our next session on KNN. Okay.
Yeah.
Fine. Thanks, Karthik. Bye.
Bye.